instruction cycle state diagram. There is first instruction fetch. Once the instruction is fetched, instruction operation decoding needs to understand what is the opcode means. Then there is operand address calculation to make sure that the microprocessor has get the address of each operand. If there are many operands, they need to fetch operand for each operand. Now there is data operation. Well, the instruction is applied to the data to execute its task. There is then operand address calculation. Have to store the operand. The operand stored here means store the result. Means that if there are many multiple operands, we have to also have multiple results as well. For a string, it has to return here for operand address calculation, and instruction is completed, then it has to fetch the next instruction. We have data flows. This is also very important. For fetch cycle, we have PC, which fetch the address of the next instruction. It is sent to the memory address register. Then the memory address register, we share these address to the memory. Then the memory will send back the data or the operand to the memory buffer register. Then the instruction fetch is going to be stored in instruction register. Then the PC is incremented to point it to the next instruction to be fetched from the memory, and so on and so forth. So this is the data flow for fetch cycle. This is very important. So we have the data flow for indirect cycle when it has fetched from the memory. Now we have the address that needs to be sent to the memory address register. The memory address register, we send it to the memory. Then the memory we get back to the memory buffer register. Then we have the CPU which has to execute the instruction. Timing diagram for instruction pipeline. We have seen that the pipeline is there to execute multiple instructions at the same time. Now, imagine we have the instruction cycle, fetch instruction, decode instruction, calculate operand, FO, fetch operand, execute instruction, then write operand. So these are 1, 2, 3, 4, 5, 6. We have 6 states. Now for the instruction number 1, time 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on and so forth. So we have instruction number 1, which is instruction fetch in time clock cycle 1. In the clock cycle 1, then we have instruction number 2, which goes in instruction decode. Then instruction number 2, we start here fetch instruction. Then our instruction number 1, we go to the calculate operand stage. Then instruction number 2, we go into decode. Then instruction number 3, we start here instruction fetch. Then we have fetch operand for instruction number 1. Then instruction number 2, we go for calculate operand. Instruction number 2 we start is decoding stage. Instruction number 4 is in instruction fetch. Then instruction number 1 will be in execution instruction. Then fetch operand for instruction number 2. Then calculate operand for instruction number 3. Instruction number 4 should be in decode instruction. Then instruction number 5 start fetch instruction. We have here, we have our instruction that's gonna write result. It's gonna write result. It's gonna write result here. It's gonna write result. Write result. 3, 4, 5. This is 5. This is 6. This is 7, 8, 9, 10, 11. Now we have this instruction cycle. So also make sure how this instruction can be executed in the same clock cycle. Clear? Clear for this diagram? Question? Clear? Alright, we have pipeline hazard, data hazard, resource hazard, and the control hazard. A hazard occurs when there is a pipeline or portion of the pipeline which has to wait for some condition that don't execution because maybe they need to operate on the same data or they need the same resource. Now, when we have resource hazard, you see here, this instruction was supposed to start here, but it has to wait because of the source offset in the memory. So waiting is there. So we have 5-stage pipeline. This is the ideal case, as we have seen in the previous slide. Now here we have idle. We have the microprocessor which needs to start because there is source offset in memory. So here it has to wait for 1 clock cycle because there is a resource hazard. For data hazard, this occurs when there is a conflict in accessing an offline location. For example, we have this data dependency. You see here, it was supposed to do is fetch offline in clock cycle number 4, 5. So it has to be idle in these 2 clock cycle because it wanted to get this data from the previous operation. This is what we call data hazard. The second instruction depends on the result of the first instruction. That's why it has to wait until the first instruction is done to get its result to be used in its instruction. Now we have pipeline hazard, which can be solved by forwarding or bypass. Now here this is without forwarding. Here this is with forwarding. You see here, instruction fetch, instruction decode. Here there is execution. So once this instruction has got the operand for this instruction, it can be forwarded to the next instruction to avoid that, to avoid long waiting. Control hazard is also known as a branch hazard, which happens when the pipeline mispredicts a branch. So as a result, there is incorrect instruction which has to enter the pipeline. Now we have to deal with these branches by using these following techniques, having multiple streams, prefetch branch target, loop buffer, or branch prediction. You can see more details in our previous lectures. Now, interrupt. Interrupt is a mechanism which happens when other modules like input-output may interrupt normal sequence of processing. Let's say there is an input module that needs to get attention of the microprocessor, then it send an interrupt. We have different types of interrupt: program interrupt, overflow, for example, overflow, division by 0, timer. We have input-output interrupt. This is from the input-output controller, input-output modules. Now, what does this mean to the user? From the user is view. An interrupt is just a stop of the normal execution of the program. Now, you see we have the user program at time 1, it's normal, time 2, it's normal. At time I, there is interrupt. This interrupt happens. When this interrupt happens, the microprocessor needs to handle this interrupt and comes back after this interrupt is handled, comes back to the normal execution of the program. So from the user is point of view, interrupt is just a interruption of normal execution of the program, then the user has nothing to do about that. Now we have the same instruction cycle state diagram, but this time we include interrupts. You see we have interrupts here. We have instruction fetch, instruction operation decode, operand address calculation, operand fetch. If there are multiple operands, you see we have the fresh, the allows which goes and come back. Then we have data operation when the instruction is applied to the data fetched from the memory. Then we have operand address calculation. We needed to store the operand. We needed to store the result. Then check if there is any interrupt. If there is an interrupt, it has to be handled before the processor fetches the next instruction to be executed. So the only thing that has been added to this diagram is this interrupt part. Make sure you do understand the instruction cycle without interrupt and the instruction cycle with interrupt. Clear? Hello? This is very important. You need to make sure you do understand this. This diagram, and this one, there is a slight difference. There is a slight difference. You see here, we don't have interrupt. This is without interrupt. And this one, this is with interrupt. That means after the execution of the first instruction, the microprocessor needs to check if there is any interrupt. If there is interrupt, it has to handle the interrupt before it fetches the next instruction from the memory. Now we have sequential interrupt processing. User program. Now we have user program doing very well. At a time I, there is interrupt X, so it has to handle this interrupt. Then once the program, the microprocessor has finished to handle this interrupt, it goes back to continue the execution of the user exit program. If there is any other interrupt, in this case we have interrupt Y, the microprocessor will go and handle this interrupt Y. So interrupt Y will be handled. Then it has to come back to handle the user exit program. So sequential interrupt in this processing. It has to be processed in the order they have been received. Now, interrupt X came before the interrupt Y. That means the microprocessor needs to handle this interrupt before this one. In the order they have been received. Now, they can be nested interrupt processing. We have a user program here. Now, at a time I, there is a interrupt X. Interrupt X that needs to be handled. So while the microprocessor is handling the interrupt X, there is another interrupt Y. So you see, it has to handle the interrupt Y before it finishes handling the interrupt X. This is what we call nested interrupt processing. Nested interrupt processing. We have sequential interrupt processing, which means the interrupts are being handled by the microprocessor in the order they have been received. Then we have the nested interrupt, where you see that while handling the interrupt Y, another interrupt X happened, then the microprocessor needed to handle this interrupt before it finishes. That means here, the microprocessor was handling the interrupt X, then another interrupt Y happened. It has to interrupt the execution, the processing of the interrupt X to handle the interrupt Y. This means higher priority interrupt can be handled before the lower priority interrupt. Now, memory system. We have started the memory system. We learned about different levels of memory. We learned about what is a memory. We learned about different levels of memory, starting from registers. We have registers. We have cache memory. We have main memory. We have second storage memory to store data permanently. We may also have tertiary storage memory depending on the technology. Now, given the number of bits in data word, given the total number of bits in address bus, given the total number of bits in data bus, address bus, we can calculate the total number of words in memory. Number of bits in data bus, let's say is 16. Number of bits in address bus is 11. We can calculate the total number of words per byte, total number of bytes per word. We can also calculate the number of bytes in memory. Number of bits in memory, and hope that everybody knows how to calculate all these memory specifications, because we have done an in-class quiz on that. All right. Memory levels. We have registers, which are really small memory inside our microprocessor. They are really fast, which are there to store data and instruction being executed by the microprocessor. Then we have different levels of the memory. Cache memory, level 1 cache memory, level 2, level 3, depending on the technology. So, cache memory is there to store the most frequently used data and instructions. Then we have main memory to store active data. All these types of the memory that we just talked are volatile memory. Volatile memory. That means they can only hold data when the power is supplied. If there is any interruption of the power, that means they're gonna lose the data stored on these volatile memory. And also there is no volatile memory. This is for temporary storage. No volatile memory. Permanent storage. Okay? So as the size of the memory increase, the speed decreases as well as the cost per GB. This is very important. We needed to take into consideration the size, the cost, and the density for the memory. Now we have DLAM structure. We have talked about two different of LAM, random access memory, DLAM and SLAM. For DLAM, it includes the storage capacitor to store data as charge. That means that it has to be refreshed periodically to retain the data. Whereas for the SLAM, it does include 6 transistors to store data in the logic form configuration. It doesn't need to be refreshed to retain data. So we have the left inverter made by T1 and T3. We have right inverter, which is consist of T2 and T4. We talked about 16 megabyte DLAM memory organization. You see we have the low address buffer and the current address buffer. We have also the refresh counter. We have the refresh circuit because it's made of DLAM, need to be refreshed. So it has the colon address swap and also low address swap. So this is the signal to the DLAM to reach the low address. Once the low address is selected, so the current address slope needs to select the colon for a specific memory source. As we say, there are a big number of words in the memory. So the CPU needed to select 1 word out of million of words. Now, error detection and the correction code. We talked about parity check, which is really simple techniques to detect the error in the data. It doesn't correct it, so that's why we need to learn more advanced error correction and detection code. So we have the parity, which needs to add the 1 extra bit to the data to check the parity. The memory controller, we add 1 extra bit to the data at the time of writing data to the memory. Then it has to check the parity when it comes to read the data from the memory. If there is no difference, that means there is no mistake. If there is any difference in the data, that means there is a mistake, but it doesn't collect. So it has only to check the parity. All right, now Hamming code. Hamming code. So for Hamming code, we needed to calculate the number of check bits that needs to be added with the data. With this formula, this inequality needs to be satisfied. 2 to the power of k minus 1 is greater or equals to m plus k. Now, if we have m equals to 8, we need k equals to 4. 2 to the power of 4 minus 1 is greater or equal to 4 or 8 plus 4. So we need 4. We need 4 check bits. So the percentage of increase is 4 divided by 8. That is 50%. For 16-bit data, we need 5 extra check bits. We need the 5 check bits that need to be with the data. Then the percentage of increase is 31.25. Now we aim to create a for syndrome for an 8-bit data weight with the following rules. All zeros in the syndrome means there is no mistake, there's no error. 1 bit set to 1 in the syndrome means there is a single error, and it has been happened in the check bits, and more than one bit is one in the syndrome. That indicates there is a mistake, and it has been happening in the data, and it needs to be collected. Now, we have 12 bit position. Here we have 12 bit position because we have 8 plus 4. We have 8 bit position. Now we need the position number. This is the binary representation of the bit position. We have the data bit, then we have the check bits as well. So we need to calculate C1, C2, C4, C8. Has everybody understood how to get C1, C2, C4, C8? From the last class, right? Yes or no? Because we're going to do a short in-class quiz, make sure you have understood this. Please take a picture of this screen. Take a picture. You may need it for your quiz, since we don't have enough time, because you needed to draw this table. Now, you can have this table, but during your exam, make sure you do remember how to make this table, because I want to give you this table. Okay? Clear? During your exam, you have to draw this table by yourself. Now we have each one. Everybody has got how to calculate this. If you have any issue on how to find this, tell me. I'm going to show you. Because for this course, there is no formula sheet. You needed to understand how to calculate this, because it's quite easy. Clear? Do you still remember how to calculate this? Huh? Do you still remember? Okay, if you remember, tell me. Don't see your mobile phone, okay? From this table, C1 is D1, yes, D2, D4, D5, that's all. Okay, C2, D1, D3, D4, D6, D7. Okay, C8, D5, D6, correct, D7, D8, correct. So we have a very short in-class quiz. Here we go. Quiz number 7. Take a piece of paper.